Alright, these are some additional notes in 6.1, and I actually included some on 6.2 also. So we're talking about exponential functions in this information. Those are functions that have a constant percent of change. So when we were talking about linear functions, there was a constant value, we called it the slope, that affected the change of the line. But with an exponential function, there's a percentage that it changes by. So one of the big examples that you'll see with it is calculating compound interest. You'll also see it with population growth, and especially in science with bacterial growth or growth of a fungus in a dish or something like that. So there are a couple different formats that you'll see for these functions. The first one that you see here, y equals a times b to the x power. That's why these are called exponential functions, because they're raised to a power. It's b raised to the x power. So a is the initial value, the starting value, whatever amount you deposited in the account or something like that. B is the growth or decay factor, and x is the amount of time. So b could be 6% and the time could be 1 year or 5 years or something like that. Another format that you'll see is what we call a closed formula, and in this formula it's written a little bit differently. So p sub 0 is the initial investment, so that would be your starting value. R is your interest rate, and T is your time. So we're going to do both of these in just a second. A third way of writing this is, sometimes we refer to this as a continuous growth. You will see these when you do Excel spreadsheets, and we're going to do a couple examples of Excels. A again is your initial value. E is a value called Euler's, E-U-L-E-R-S, Euler's number, and it's 2.71828. If you look on a calculator, most calculators have a button. You'll notice right here on the division sign, right above that, there's a little E. And if I use that E in my calculator, notice how it says E, and if I press enter, it says 2.71828. So Euler is a value, it's like pi. K is the continuous growth rate, and X is your time. So let's do an example. So here we have, you deposited $500 into a savings account, an annual percentage rate of 6%. How much money do you have at the end of 5 years? So we started off with $500. My interest is principal times rate. So the principal is the $500, the rate is the 6%. If I put that in my calculator, I get 30. So at the end of 1 year, I have $530. Okay, so we're not going to look at this for a second. Let's just keep going. So that means at the beginning of year 2, I have $530. So when I calculate the interest, I'm going to calculate it using the 530. So the second year, I get $31.80 in interest. So now the balance in my account is $561.80. And then I continue to repeat that process. So I bring the $561.80 down. My interest is 33.71. My new balance is $595.51. I bring that down. I calculate the interest. I add that in. I get $631. I bring that balance down, I calculate the interest, and I add that in, and I get $669. So at the end of 5 years, I will have $669.14 in my account. Okay, so here we have the closed formula. Remember, we talked about this closed formula up above, and we have what we refer to as a recursive formula. So with a recursive formula, instead of multiplying and getting the rate and then adding it in, I'm sort of combining these two steps together. So I'm going to take the 500 and I'm going to multiply it by 1.06, and I get 530. And then the next time I calculate, I'm using 530 times 1.06, and I get 561. And then the next time I use 561 times 1.06 and I get 595.51. Now notice my numbers are all pretty much the same as I'm going through here. They change a little bit right here, and this is just because of rounding off. On these problems over here, I rounded off my interest, and on these problems over here, I'm not rounding anything. So I end up in the very end with 669.11. So again, it's just a rounding off issue that caused the change. Okay, and then with my closed formula, it makes it even easier. So the 500, so let's look at this. In my closed formula, the initial value is 500. 1 plus the rate, which is 6%. And then raised to the t. T is the number of years. So on this first one, if I do a little bit of reducing here, I get 1.06 raised to the t power. So if you look at this first formula, I'm doing 500 times 1.06 raised to the 1 power, which is 530. And then I do 500 times 1.06 raised to the second power, which is 561. 500 times 1.06 raised to the third power is 595. So that little symbol that I'm using there, we refer to that in math as a caret. So if I do 530 times 1.06 raised to the second power, and I'm using this button right here, that's the caret symbol, or the exponent, that's where I get the 595.51. And then I repeat the process 2 more times. So there's different ways of getting the formulas. If I asked you how much money did you have in the account at the end of 10 years, instead of going through this recursive method where I have to do the calculations 10 times, I could just go straight to the closed formula and put in 500 times 1.06 raised to the 10th power, and I don't have to do as many calculations. Alright, so this is just a little bit more of an explanation of the recursive formula. So the recursive formula, the p sub t plus 1 is the new value, and 1 plus the rate divided by 100, that's where we get the 1.06. And then multiplied by the old value. So we took the 530, we brought it down, and we multiplied the, sorry, I'm right here. You took the 530 and brought it down and multiplied the next time by 1.06. And then you took the 561 and brought it down. So this is called recursive because you have to keep using the value that you got before. Whereas the closed formula, to get the new value, you just take the original value times 1 plus rate over 100 raised to the t power. I'm going to do a couple more examples on the next video, so keep an eye out for that.